Pleasure to have Daniel Kuhn presenting in our colloquium today. Daniel is a professor of operations research at the College of Management of Technology at EPFL. There he is the chair of risk analytics and optimization. He serves as the area editor for optimization at ORIE. And you may know him because he and his group have won numerous awards, and they've really done some of the most foundational and exciting work in data-driven optimization under uncertainty. So it's a real pleasure to have him here today to tell us about a paper that seems like a very cool and very exciting, very ambitious title, a general framework for optimal data-driven optimization. Please, Daniel, go ahead when you're ready.
Thank you very much, Nathan, for the kind introduction, and in particular for the invitation to give this seminar. It's a great honor, and pleased to see many people that I know in the audience. So, my talk is joint work with Tobias Sutra and one of my postdocs, and with Bart van Parijs from MIT. And in this talk, I would like to address, I would like to construct data-driven decisions for stochastic optimization problems that in some sense make the best possible use of the available data. So in some sense, we'd like to develop optimal or efficient estimators for the optimizers and the optimal values of stochastic optimization problems. And I would like to develop such a framework, a well-defined framework when I can analyze these questions that is general enough for interesting applications. So the framework I'd like to propose consists of three primitives. And the first one is a stochastic optimization problem that reflects a ground truth against which our data-driven, our estimators will eventually be assessed. The second ingredient is a family of probability measures that captures structural information about the uncertainty. And the third ingredient is a data-generating process that generates training samples. So let me talk about the stochastic optimization problem first a bit. So here, it's just a problem that minimizes some generic objective function that depends on the probability measure that governs the uncertain problem parameters. And examples include, for example, the expectation or some risk measure of an uncertain loss function. Another example might be the conditional expectation of an uncertain loss function given contextual information. Or another example might be the long-run average expected cost of a parametric control policy. So we try to be very general here. Now, the crux of data-driven decision-making is that the probability measure that governs the problem parameters is not known to us. We're going to assume here, however, that we know that the data-generating probability measure belongs to a parametric family. And we're going to assume that all probability measures in this family are defined in the same sample space. And I'm going to assume that these probability measures are parameterized by a finite dimensional parameter theta, which ranges over some convex set capital theta. Now, even though the true probability measure and the true parameter theta encoding this measure are unknown to us, we have access to training samples that can be used to learn theta. So we look at different data generating processes in this talk, and some examples we will look at are very simple processes of independent observations on finite state spaces. We'll also look at finite state Markov chains. We'll look at certain vector autoregressive processes, and we'll also look at some i.i.d. processes where the observations, they belong to some parametric distribution families like normal or exponential distributions and so on. But these are just some examples, so the framework is hopefully more general to capture other settings. And I would like to emphasize that you see from these examples that we do not insist that the training samples are mutually independent. So the Markov chains and autoregressive processes, of course, they have serial dependence. Throughout the talk, I would like to use some color coding. I'll use black symbols to denote deterministic known quantities. I'll use red symbols to denote unobservable quantities, like probability measures typically, and blue symbols to denote observable functions that are basically functions for the training samples. Okay, so to make things a bit more concrete, let me give you a simple example of this general framework. The classical Newslander problem, which formalizes the fundamental dilemma of the seller of a perishable good. So this perishable good usually is seen as a newspaper, which of course becomes completely worthless at the end of the day. So let me describe first the stochastic optimization problem. So in the morning, the news vendor buys newspapers from the publisher, and the order quantity is denoted by X, can be any integer between 1 and t. During the day, an uncertain demand is observed, and we assume here also that this demand may take any value between any integer between 1 and t. And then the news vendor sells papers until either the inventory or the demand is exhausted. So the sales quantity would just be the minimum between X and Xi. So the overall goal would be to minimize expected costs, and here the expected cost is this expression here. So you see that we have K here denotes the wholesale price. This is what needs to be paid to the publisher. P is the retail price, should be bigger than the wholesale price, which is what is charged to the customers. The first term here is the order cost, so just price times quantity. The second term is the profit from sales, just the retail price multiplied by the sales quantity. The expectation here is evaluated with respect to the distribution of the demand. Now, the crux of data-driven optimization is that we do not know the demand distribution, but we assume that we have access to historical demand data that allows us to learn about this distribution. So in particular, we're going to assume that we have access to a finite sequence of historical demands, Xi, which are generated by some stochastic process. Now, the probability measure that governs the stochastic process is unknown, but we assume that it is known to belong to some parametric family, like before, encoded by some finite dimensional parameter vector theta. In particular, in this example, I'm going to assume that under every probability measure, the historical demands are independent and identically distributed. And I'm also going to assume that the parameter vector theta just captures the true probability mass function of the demand. So basically, the components of this d-dimensional vector, they represent the probabilities of the different demand levels. And now the goal is the news vendor needs to decide how many newspapers to order. This cannot be done because the true stochastic program cannot be solved because theta is not known. So the news vendor should actually construct somehow a surrogate optimization problem constructed from the observable data. So the problem should only depend on the data, but not on the theta, and then get a data-driven decision this way. Okay. So in this talk, I would like now to address the question, how can we construct such surrogate optimization problems in some sense, maybe optimally? So in general, just let's remind ourselves that what we actually want to do is we want to solve this original optimization problem, which depends on the true probability measure or its parameter, which we do not know. Since we do not know this one, but we have only access to t training samples, we could use some methods from statistics, like maximum likelihood estimation, to construct some statistic theta hat t. So you should think of this theta hat t just as an estimator for the unknown theta. And of course, we simply could just plug this estimator into our optimization problem instead of the unknown theta, and then solve this problem and thereby get the data-driven decision. Now, this is just one way of constructing a surrogate optimization problem, but in this talk, I would like to adopt a more broad perspective, and I would like to allow you to construct surrogate optimization problems much more generally. So basically, the objective function, here denoted by c hat t of the surrogate optimization problem, we should allow it to be built in any way we want from the t-training samples. Okay? And let me give you some examples. Actually, there is a lot of literature. People have come up with many different ways how to construct data-driven, how to construct such surrogate optimization problems. The oldest and most popular approach is the sample average approximation, which basically just evaluates the objective function under the empirical distribution of the training samples. But some people have also proposed to add a regularization term to this empirical risk that hopefully, the hope is that this would improve out-of-sample performance. There is also a so-called predict and optimize approach, which is basically what I've shown you at the beginning. So you just use some method of statistic to estimate, to construct an estimate for theta and plug this into the original objective function. Now, you could train this estimator just simply in view of a generic loss function like the mean squared error, or you could also train it in view of actually the cost function that you would like to minimize eventually in the optimization model. You could probably also come up with some neural network that maps the training samples to an estimated objective function c hat t, or you could use some methods of distribution robust optimization. So here the idea is to construct a family of distributions such that under each of these distributions in the family, the observed training samples are in some sense sufficiently likely. And then you could construct an objective function that evaluates just the worst case objective over all distributions in the family. And again, there is a huge literature on how you could use data to construct such distribution families or ambiguity sets. Yeah, but I mean, these are just ways how we construct such surrogate optimization problems. Probably there are many, many more, and I don't even try to enumerate everything, or there's probably many things that people have not even thought of. So just to make things clear, I would like to introduce some terminology. So I would like to refer to c hat t as a data-driven predictor. So that's the objective function of our surrogate optimization problem constructed from the PT training samples. And of course, this c hat t predicts the risk of any fixed decision in view of the training samples. And it uniquely determines the surrogate optimization problem. Now, any minimizer of the surrogate optimization problem I call a data-driven prescriptor, and denoted by x hat t, because it prescribes a feasible decision in view of the t training samples. And at this point, I'm always going to assume that the prescriptor is the minimizer of some predictor, but I would like to point out that this is a very weak requirement. In fact, any function that maps the samples to a feasible decision can be represented as the minimizer of some data-driven objective function. So in that sense, the prescriptors can at this point really be perceived as almost any function that maps the training samples to a feasible decision. So it's very general. Now, in the talk here, I would like to discuss how we can construct data-driven prescriptors, predictors and prescriptors, somehow in an optimal manner. And to compare different prescriptors and predictors, I would like to use 3 different performance measures. So the first one is just the in-sample risk, which is the optimal value of the surrogate optimization problem. So it's basically just the objective function evaluated at an optimal solution. And this in-sample risk is accessible to us because it's just constructed from the data, and there's no quantity that we do not know. The second performance measure is the out-of-sample risk, which is actually the true risk of the prescriptor x hat t under the unknown true probability measure encoded by theta. Now, the out-of-sample risk is not accessible to us because we do not know the true theta. At this point, I would like to point out that the in-sample risk is not uniquely determined. In fact, any fixed prescriptor, so any fixed data-driven decision, can be explained by many different objective functions or predictors. Very simply, we could just add a constant to c hat t, and this would not change the optimal decision. So that means that if we wanted to construct a predictor that has the smallest possible in-sample risk, this would be a nonsensical problem unless we somehow restrict the way we are allowed to choose the predictor, right? So if we wanted to minimize the in-sample risk, which is accessible instead of the out-of-sample risk, this could be nonsensical unless we restrict our choice of the predictor. And for this reason, I would like to introduce a third performance measure, which we call the out-of-sample disappointment. So this is the probability that the out-of-sample risk strictly exceeds the in-sample risk under the unknown probability measure. So if the out-of-sample disappointment is high, this means that it's very likely that our prediction in the in-sample risk of the of our prediction of the risk is smaller than the actual risk we will face out of sample, which actually lulls the decision maker into a false sense of security and will lead to disappointment in out of sample tests. So the out of sample disappointment is also not accessible to us because it also depends on the unknown theta. Now, generally, we would like to find predictors and prescriptors, or the surrogate optimization problems that they use, that make somehow all of these three performance measures small. Now, I would also like to point out that there is a basic trade-off between the in-sample performance and the out-of-sample disappointment. So if I would like to make the in-sample risk smaller, and a very simple way to do that would be to add a negative constant to it, to the predictor, right? Then invariably, this would mean that we make the out-of-sample disappointment higher. Okay, so the probability that will be disappointed out of sample will grow in this way. So this means that it will actually be challenging to make both of these quantities small at the same time. Okay, so on this basis, well, before I tell you how we actually construct such hopefully optimal surrogate optimization problems, let's go back to the newsvendor problem and let's look at some examples. So let's look at some particular predictors and prescriptors. So there will be three charts. In the left chart, I will show you for each predictor and prescriptor how the out-of-sample disappointment changes with the number of samples. In the middle chart, I will show you how the in-sample risk changes with the number of samples. And in the right chart, I will show you the trade-off between in-sample risk and out-of-sample disappointment. So a particular predictor and prescriptor will be visualized by a point in this right chart, and the x-coordinate will be the exponential decay rate of the out-of-sample disappointment. We want the out-of-sample disappointment to be small, so we want it to decay as we accumulate more training samples, and therefore a higher decay rate is better. So we want to be on the right-hand side. The y-coordinate will be the asymptotic in-sample risk, and this one we want to be small. So let's look at the first example. Model 1 is just the sample average approximation model, where the predictor is set to the empirical risk, so the actual risk evaluated under the empirical demand distribution, which is here denoted by theta hat t. So this is the newsvendor problem where we minimize expected cost. And in this case, the out-of-sample disappointment does not decay at all, because this is a consistent estimator, and the central limit theorem tells us basically that the out-of-sample disappointment must converge to 1/2 as the number of samples increases. The in-sample risk is relatively small and saturates quickly as the number of samples increases, and the brown dot on the right-hand side here, so this one visualizes this particular model. The decay rate of the out-of-sample disappointment is 0 because the out-of-sample disappointment actually does not decay to 0 at all. So if we wanted the model, the out-of-sample disappointment to decay, we could look at a simple variant of this SAA model. We could just actually add a positive bias term to the predictor, here denoted by R. So this will make the model more conservative, and it will actually ensure that the out-of-sample disappointment will decay to 0, but it will also make the in-sample risk higher. So the dashed line in the right chart visualizes the different models obtained in this way if R is swept from 0 to plus infinity. And you can see that there is a trade-off. So the higher the R, the more conservative the model is. The in-sample risk goes up, but at the same time also the exponential decay rate of the out-of-sample disappointment becomes bigger. So we have more certainty that the in-sample risk does not underestimate the true risk. Let's look at the third model, and this one is a distributionally robust model with a moment ambiguity set. So here, the objective of the surrogate optimization model, the predictor, evaluates the worst case expected newsvendor loss over all distributions that have the same first 4 moments as the empirical demand distribution to within a certain tolerance R. And if I make the R bigger, of course, the set of distributions becomes larger and the supreme gets bigger, so the model becomes more conservative. So we tested this first for 3 different R's. The green lines and the green dots, they represent a small r. The light blue, they represent a medium r. And the dark blue, they represent a large r. You can see as r gets larger, the in-sample risk gets higher, but the out-of-sample disappointment decays faster. So on the left chart, we have a log scale, and the out-of-sample disappointment here describes essentially, in each case, a line, and the slope of that line is the exponential decay rate of the out-of-sample disappointment, which is actually the x-coordinate of the dots on the right chart. We can just, again, sweep R from 0 to plus infinity, and then all models obtained in this way, they will trace out the dashed dark blue line in the right chart, which completely characterizes all the models for all the performances we can obtain in this way. Now let's look at the 4th model even. So this is again a distribution robust optimization model, this time with a Wasserstein ambiguity set. So we evaluate for any fixed x the worst case expected loss over all distributions within a Wasserstein distance of at most r from the empirical distribution. And the orange dot that you see on the right chart here corresponds to a particular choice of the radius. And here the decay rate of the out-of-sample disappointment is the same as for the moment ambiguity set with a big R. So it has, well, in terms of disappointment, it's equally good, but it's actually better in terms of in-sample risk. You see the in-sample risk is smaller than the other one. Now, if we sweep R again from 0 to plus infinity, then all the different models obtained in this way, they trace out the orange line in the right chart. Unsurprisingly, if we set R to 0, then just we recover the sample average approximation model. So we start at the brown dot. What we also observe is that the Wasserstein model dominates all the other models we've seen so far, because for any fixed decay rate of the out-of-sample disappointment, we get a smaller in-sample risk. So in that sense, we get a better trade-off. So this model dominates the others.
Oh,
the 5th question, yes?
I'm sorry. Please just maybe respond when there's the right moment. But when I look at the 3 panels here, for the news vendor problem, we actually do know the optimal solution. So we could look at the out-of-sample, sorry, I can't remember what you called it, but the out-of-sample, I think it was the out-of-sample risk.
Yeah.
And that would be, in some sense, what many traditional people in optimization would view as the right quantity to look at.
Absolutely, absolutely. And I would like to, maybe we can talk about this a bit later, because I'm going to talk about this. I will explain why I look at these 2 measures, in-sample risk and out-of-sample disappointment instead of the out-of-sample risk. So I will explain that just in a few slides.
Okay, thank you.
Yeah. That's okay, yeah.
And Daniel, while we're already stopping you, I'll chime in with one quick question. So if you look at model 4, the one you just showed, I think this connects to Shane's question as well. I mean, I think you're on paper that you cite, you with payment, you showed that in terms of the prescriptor, the SAA prescriptor and the Wasserstein prescriptor are the same regardless of R. That's something that you proved, right? For the news vendor problem. I think it's a consequence of one of your theories.
For the news vendor problem, okay, but we prove it that this is the case when the demand distribution is the whole, I mean, it can be supported anywhere in the whole space. Now here it's a discrete version of it. So it's actually also not completely correct that I cite my paper here, because we looked at the continuous support case.
Okay, so it's only for the continuous support. But in either case, I feel like that brings up the question of,
so
they have to be the same as the performance evaluator. I can just do SAA and use Wasserstein as a performance evaluator.
Yes, but you see, actually the same is true for the biased SAA. We just added a constant to the objective function. This did not change the decision. So in terms of out-of-sample performance, you're right, you will get the same out-of-sample performance. However, the out-of-sample disappointment gets smaller, and it's still a good thing, I would argue, because then you get more confidence that your predicted risk is actually a safe approximation of the true risk you will be facing, and it's not just an arbitrary number that doesn't tell you anything.
Yeah, but I could use the same Wasserstein only after choosing an X, right? To make a confidence interval.
That is true. Yeah. So at this point, we should just see this as a, as a visualization of what happens with respect to these performance measures. So
can I ask a quick follow-up?
Yeah, sure.
Actually, this I think is a follow-up to Shane's question. So are you assuming that the planning problem, or like the solution to the optimal policy given the randomness? Or like are you simultaneously?
I should say, in all the examples here, I assume that the demand distribution is a uniform distribution of the integers from 1 to d. So I know the true distribution. Of course, these models, they don't know it. So I would know what the optimal solution would be in this case.
What I meant is you also know the policy which maps the state to the actions for these problems. So if
what here? You mean
I guess the current budget. Well, not the training samples, the state of the control problem itself.
It's not a control problem, right? It's a static problem. So we don't have a state.
Oh, so you're just solving the one shot.
It's one shot. Yeah. It's very simple.
See. Okay, sorry. Okay, maybe that's also Shane's question then. Okay, all right.
Yeah. No worries. Okay. And so the last model I wanted to show to you is the distribution robust model with a Callback library ambiguity set. So it's like the Wasserstein ambiguity set. We look at the worst case expectation over all distributions in some within some radius of the empirical distribution, but this case we measure distances with respect to the Callback library divergence. And again, if the radius is set to 0, then of course we just recover the sample average approximation model. And if R increases, then we will get a more conservative model. So again, the in-sample risk will increase and the decay rate of the out-of-sample disappointment will also increase. And the red dashed line in the right chart visualizes the trade-off between these two quantities. And we can see now that actually this model dominates all the others. So in some sense, that's if we want to use these two performance measures, then this one is the one that has the best trade-off. Okay, so the two things I would like to observe here: different models can perform very differently, and different predictors can perform very differently with respect to these two performance measures, so the asymptotic in-sample risk and the asymptotic exponential decay rate of the out-of-sample disappointment. And the other thing that is noteworthy is maybe that in the leftmost chart, the out-of-sample disappointment is in all examples almost the perfect line of the number of demand samples. And that means that this exponential decay rate almost perfectly captures how this out-of-sample disappointment behaves. Okay, so it's a good proxy to capture this probability. Okay, so now how could we go about to construct optimal, in some sense, surrogate optimization models? And as you say, the true goal would be to minimize the out-of-sample risk. So to find a prescriptor x hat t constructed from the data that minimizes the out-of-sample risk in some sense. Of course, since x hat t is a feasible decision, we can never do better than the theoretical minimum, which is the optimal value of the original stochastic optimization problem. Now, I would like to focus on predictors and prescriptors that have a small out-of-sample disappointment, which means that the probability, we have a high probability that the in-sample risk exceeds the out-of-sample risk. And that also means that the expected in-sample risk with respect to the probability measure corresponding to theta is also an upper bound with high probability of the out-of-sample risk. Now, if we try to construct a predictor that has a small in-sample risk, but at the same time we try to maintain a small out-of-sample disappointment so that the in-sample risk stays above the out-of-sample risk, then we're basically, by pushing down the in-sample risk, we'll implicitly also push down the out-of-sample risk. So graphically, constructing a CRT with a low in-sample risk while maintaining a small out-of-sample disappointment will implicitly push down the out-of-sample risk, hopefully close to the theoretical minimum. Now there is an issue here. Of course, the out-of-sample performance depends a lot on theta, which we do not know, and it can be quite different for different thetas. In fact, there are infinitely many thetas, and we should think of it as some continuous function of theta. Also, the theoretical minimum of our stochastic optimization problem depends on theta, so that's just some other line. And the expected in-sample risk depends on theta because it depends on the probability measure that we use to calculate the expectation. So this is also another quantity that is a function of theta. Now, if we do not know which one is the true theta, what we could try to do is we could try to push down the in-sample risk simultaneously for all theta, while trying to ensure that the out-of-sample disappointment remains also small simultaneously for all thetas. Graphically, this would amount to trying to push down simultaneously the in-sample risk everywhere. Keeping the out-of-sample disappointment small would therefore mean that we implicitly also push down the out-of-sample risk uniformly across all thetas. And if we manage to do that, then we would also do it in particular for the theta that is the true one, which we do not know. Okay? So this is what we ideally would like to do. And let me now formalize this. So I would like to set up an optimization model that finds the best possible surrogate optimization model as described by a data-driven predictor, C hat t, and the corresponding prescriptor, X hat t. Now remember that C hat t and X hat t are constructed from the t training samples. So these are functions of t samples. So these are complicated objects. And what we would like to minimize in this problem is the asymptotic expected in-sample risk. Now, we would like to minimize this in-sample risk simultaneously for all theta in the parameter space. So this is a multi-objective problem with infinitely many possible objectives. The constraints in this problem, they're designed to keep the out-of-sample disappointment small. So what the constraint basically says, if you ignore the lim sup for a moment, you could multiply the capital T to the right-hand side and exponentiate both sides. Then you would see that, well, the constraint just says that the out-of-sample disappointment, the probability here, should asymptotically be smaller or equal to e to the minus RT. So as the number of training samples increases, this should decay exponentially at the rate R. R is the only free parameter that we need to specify as a user here in this problem. Now, of course, if we try, so this is a multi-objective optimization problem to hopefully construct optimal predictors and prescriptors. But usually in multi-objective problems, if we try to minimize one objective function, then we may well deteriorate other objective functions. So for example, graphically, if we try to minimize the expected in-sample risk corresponding to theta 1, right? So we push down this objective function. What may happen very well is that we will deteriorate, say, the objective function corresponding to theta 6. And since we don't know which one is the right one, this would not be very desirable. So what would be the ideal case is that we somehow manage to find or to construct a Pareto-dominant predictor, here denoted by C hat star T, which simultaneously minimizes the objective functions for all possible theta. Now, usually in multi-objective problems, such a Pareto-dominant solution does not exist, but if it does exist, then it is very nice because it will attain the best possible trade-off between in-sample risk and out-of-sample disappointment simultaneously for all theta, and therefore in particular also for the unknown true theta. Okay? So the optimization problem over surrogate optimization models that I propose to you is really an optimization problem over optimization problems, right? Over surrogate optimization problems. So actually we call it therefore a meta-optimization problem. And so this has some strengths and weaknesses, and we can later discuss about them, but strengths in my view are that this model provides a proxy for optimizing the out-of-sample risk. The out-of-sample risk per se we cannot optimize because there's true theta we do not know, and it seems difficult to do that directly. So this is a proxy of doing that. It errs on the side of caution because we approximate the out-of-sample risk from above. So by keeping the out-of-sample disappointment small, we minimize an upper bound on the out-of-sample risk, which is this in-sample risk. I will show to you later that under conditions that are of interest, this problem does indeed admit a Pareto-dominant solution, and this solution even is available to us in closed form. So we can characterize explicitly the optimal predictors and prescriptors. And in these cases where it is available, it also facilitates a separation between estimation and optimization. So I'll say more about that later. There's also some weaknesses. You can criticize that the performance criteria that we're using are asymptotic. And this is true, this is a weakness. The example, the news vendor example showed, however, that the decay rate of the autosample disappointments decayed almost precisely like an exponential function. So using the asymptotic decay rate doesn't seem to be such a bad approximation for this. Also, the in-sample risk saturated very quickly as a function of t. So also there, taking the limit maybe is not such a big deal. There is the choice of the R parameter here, which is to some extent subjective. And the bigger R, the more conservative you are, the more sure you want to be that you really approximate the autosample risk from above. You could ask, why do we insist on an exponential decay rate? Why not on something that is faster or smaller? We can talk about this later as well, but again, from the news vendor example, we've seen that actually in practice, all the decay rates were exponential. And you could also criticize that all feasible or even all optimal models, of course, are biased. They provide biased estimators for the optimal value of the objective function of the stochastic optimization model.
So, is there a reason for the? I was just looking at the constraint, and it felt like you could have used. So you've really used the L0 norm in some sense when comparing C and C hat. Would it like? Is there some reason? So, like, I'm sort of reading the constraint as looking at the expected value of the indicator that the two are not equal.
Yeah.
But I could also look at, say, the L1 or the L2 distance between them. And I mean, is that like a principal reason why the L0 makes sense here, or?
So I think you will see later why this makes sense. I mean, the reason why this problem is of interest is exactly for the reasons listed here. And I think the main beauty of this, that this indeed will admit a Pareto-dominant solution in closed form. So I would like to show to you how this, and then maybe you will appreciate why we formulate it in this way. Yeah.
Got it. Thanks.
Yeah. So before I show you how we solve the full-blown meta optimization problem, I would like to propose to you a solution to a simpler version of it. Namely, the predictors and prescriptors, they are functions of the T training samples. And as T becomes large, these objects may be difficult to manipulate or even to store. So it might be much more convenient to use the T training samples and compress them into a statistic theta hat T of constant dimension, and then just focus on predictors and prescriptors that depend on the data indirectly through this summary statistic. So this might be easier. These objects might be easier to handle. And if we do that, then, well, we can construct, or we can define so-called compressed predictors and prescriptors, which are exactly these objects. It's like the normal predictors and prescriptors, but with the additional restriction that they depend on the data only indirectly through the statistic. And we can construct a restricted meta optimization problem, which does not optimize over all functions of the data, but only over functions of the data that depend on the data through the summary statistic. Now, I would like to argue that this problem here, this restricted meta optimization problem, admits Pareto-dominant solution if the statistic theta hat T satisfies a large deviation principle. Okay, so let us remind ourselves what is a large deviation principle. So we say that the estimators theta hat T, they satisfy a large deviation principle if there exists a rate function, which I denote by capital I, such that the inequalities on this slide hold for every Borel set D, or subset of the space of parameters. Now, the first thing to notice is that the rate function I here should be interpreted as a distance measure between realizations of the statistic. So theta hat T should be a realization of theta prime, should be interpreted here as a realization of theta hat T. And a distance will be between such a realization and a theta. Now, let's try to parse these inequalities. So on the left-hand side, on both sides, if you forget the lim sup and lim inf, it's basically just the exponential decay rate of the probability of the event that the estimator will fall into this set D. On the right-hand side, what the inequality tells us that actually, so the first inequality tells us that this exponential decay rate of this probability is at least as large as the distance of the true theta that generates the data to the closure of the set D with respect to this rate function. And the lower inequality tells us that this decay rate of this probability is at least as large as the distance, the I distance between theta and the interior of the set D. Okay, so it's a bit, if you've never seen that before, then this is hard to parse. So here is a visualization of what this might look like in the case of the Newswender problem. Imagine that we have only 3 different demand levels, and that our statistic that we're considering is the empirical distribution. So its 3 components are the 3 empirical probabilities. And the realizations of the empirical distributions are then just any points in the 3-dimensional probability simplex. Now, the true demand distribution is denoted by this red dot here. And let's ask the question, what's the probability that the empirical distribution falls into the yellow set B? Now, because the demands we assume to be i.i.d, the law of large numbers tells us that with probability 1, the empirical distribution will converge to the theta. So the probability of the yellow set will eventually be 0. That is clear. The large deviation principle tells us something more, however. It tells us how the probability decays. Actually, it tells us that the probability of the set will decay exponentially at the rate which is precisely given, minor conditions, by this r, which is the distance between the point theta and the set with respect to this rate function. Okay, so that's the intuitive interpretation of a large deviation principle. Now let's go back to our meta-optimization problem, actually the restricted meta-optimization problem. And let's assume that the summary statistic theta t that we use in this meta-optimization problem satisfies a large deviation principle with respect to a rate function that also satisfies some regularity conditions. Technical thing, let's not discuss about that. And then we have this first main theorem. This tells us that under this assumption, the restricted meta-optimization problem has a Pareto-dominant solution, and this Pareto-dominant solution has a distributionally robust interpretation. So the optimal compressed data-driven predictor here is given by this expression. So it evaluates the worst case risk over all models theta in an ambiguity set described by the rate function I of the large deviation principle. And in particular, the shape of the ambiguity set is actually a ball with respect to this rate function centered at the statistic theta hat t. And the radius of the ambiguity set is exactly the decay rate of the out-of-sample disappointment that we imposed in the meta-optimization problem. So this has a clear and nice interpretation, maybe unlike regularization parameters that you use sometimes in statistics. They don't have a physical interpretation. This R here has this interpretation as the decay rate of this quantity, which we know what it is. Okay, so this is the first main result. Actually, we have some freedom in setting up the problem. So when we formulate our distribution family, we could just as well use a different parameterization, which would be obtained by applying some homeomorphic coordinate transformation on this model space capital theta. So a homeomorphism is just a continuous function, continuous bijective function with a continuous inverse. So that's the first degree of freedom. And there's another degree of freedom. Actually, we could, instead of the statistic theta hat t, we could construct another summary statistic, which is just obtained by transforming the original statistic under some other homeomorphism psi. And we would get equally valid problem formulations under such coordinate transformations. There may be others that we didn't think of. Now, what we can show is that and that's a very simple consequence of the contraction principle in large deviations theory, that this new transformed estimate also satisfies a large deviation principle, again with a regular rate function, and the formula is given here in terms of the original rate function and coordinate transformations. And what this basically means is that Theorem 1 still applies. And if you look at this carefully, you see that actually the homomorphic coordinate transformations, they have no impact on how the optimal data-driven prescriptors map the raw data to decisions. So this gives us some sort of assurance that what we're doing is something reasonable. So let me now go back to the full-blown meta-optimization problem, which optimizes not only over restricted predictors and compressed predictors and prescriptors, but over arbitrary functions of the data, right? And hopefully we can now still find Pareto-dominant solutions for this much bigger problem. And I would like to argue that we can do that under an additional assumption, namely that we have access to a statistic, theta hat t, that not only satisfies a large deviation principle, but that is also sufficient for the parameter theta. So on this slide, there's a definition of a sufficient statistic. So theta hat t is a sufficient statistic for the unknown parameter theta if the distribution of the training samples, psi1 to psi t, conditional on a particular realization of the statistic, is independent of the theta. So what this means is that if I know the summary statistic theta hat t, then I will not pay anything for getting access to the full data set. Any statistically useful information that is contained in the raw data is already contained in the sufficient statistic. And let's now assume that actually this happens. So we have access to a sufficient statistic for theta, and that this sufficient statistic also satisfies a large deviation principle with a regular rate function. Then this is our second main result here, theorem 2. In this case, the full meta-optimization problem over any arbitrary functions of the data still has a Pareto-dominant solution. And this solution still has a distribution robust interpretation. It's actually the same distribution robust predictor that we've seen before, which optimizes over, which evaluates the worst case risk over a rate ball centered at the statistic. And the radius of this rate ball is the decay rate R of the autosample appointment. So what this shows us in some sense that there is at optimality some separation of estimation and optimization. Namely, if we would like to evaluate the optimal predictor or an optimal prescriptor, then we can do that in two phases. The first one is we take the raw data and we just construct the estimator from it. So that's the estimation phase. Once we have the estimator, then we can just plug it into the DRO problem here and solve it with some methods of optimization. And these two things are separate, right? And that's the optimal thing to do with respect to our performance criteria. So I would like to mention that this second theorem here, which tells us that if you have a sufficient statistic, you cannot do better than solving this DRO problem. This is in some sense related to the classical Rao-Blackwell theorem in statistics. So what does this theorem tell us? Well, let's fix for a moment a particular x, and let's look at a predictor c hat t of x, which is actually just an estimator for the true risk of x. Now, if we had access to a sufficient statistic for theta, and the sufficient statistic here is again denoted by theta hat t, then the Rao-Blackwell theorem tells us that we can improve this estimator here, c hat t, by conditioning it on the sufficient statistic. The resulting conditional expectation is another estimator. And actually, even though it seems to depend on theta, it actually does not depend on theta because theta is a sufficient statistic. And this estimator depends on the data only through the sufficient statistic by construction. And one can show that this estimator has a smaller mean squared error than the original estimator. So in this sense, it is the better estimator. So whenever you have an arbitrary estimator depending on all the data in a complicated way, you can construct a better one, or at least an equally good one, by conditioning it on the sufficient statistic. And you might think that the theorem 2 can be proved in this way from theorem 1. Turns out it's not true. The reason is that Rao-Blackwell theorem critically relies on Jensen's inequality, which applies because the mean squared error is convex. But we deal with the autosample disappointment, which is a very non-convex function of the predictor. So actually, we didn't find a simple proof. We struggled a lot, and our proof is much more complicated than that of the Rao-Blackwell theorem. Okay.
Ask one quick question about the formulation, like the version of theorem 2 looks a lot like the rate distortion bounds. So in information theory, there's this notion of if you want to compress a data source such that you minimize some function of the compressed data, then the optimal solution is given by what's called the rate distortion solution. And it would kind of use the same sufficient statistic, but that's the sufficient statistics under the what's called the data processing inequality. I guess, like, do you know if there's any relation between the two, or?
To be honest, I don't know from the top of my head. So maybe you should give me a reference for this. And actually, my co-author's there. So my co-author has an information theory background, so I'm sure he knows. Me personally, I do not know about that very well. So to complete my talk, I would like to give you some examples of data generating processes that satisfy large deviation principles and or sufficient statistics in some cases. And these are the examples where we can actually find Pareto-dominant solutions for the restricted or for full-blown meta-optimization problem. And the first example is, again, the news vendor problem, where the statistic we're going to use is the empirical distribution. So it's a d-dimensional vector, and each component, the components of this vector are the empirical frequencies at which we observe the different demand levels. And this empirical distribution is actually a sufficient statistic for theta. This follows from the Fisher-Neiman factorization theorem. And from Sanoff's theorem, we also know that this statistic satisfies a large deviation principle. And the rate function is actually the Callback-Leiber divergence between the statistic and the theta. So that means that we can actually solve the full-blown meta-optimization problem, and that the distributionally robust predictor with a Callback-Leiber ambiguity set centered at the empirical distribution is the Pareto-dominant solution. And that is consistent with the examples that I've shown you at the beginning, where the Callback-Leiber was the one that dominated all the other models. And what we know now, based on the theory, is that no function of the data could have done better in that chart. So however we construct the CIT, any arbitrary function of the data, we would always have been above the red dotted line. So this is the best you can do. Second example would be that of a finite state Markov chain. So usually Markov chains are best encoded by the transition probability matrix. I'm going to assume here that it's a time homogeneous Markov chain. But it turns out for our purposes, it's more convenient to encode the Markov chain by the so-called doublet distribution. So that is the probability mass functions of two consecutive states in the Markov chain asymptotically as time goes to infinity. And I'm also going to assume that actually all one-step transitions are possible in this Markov chain. It's a minor assumption, I guess, because the probabilities could be arbitrarily small. Well, okay, so if you use these doublet distributions, then they would range over this set capital theta here. So they would all have to be all entries would have to be strictly positive because all one-step transitions should be possible. Of course, it's a probability mass function, so it should be normalized. And then because we're looking at the limit when t goes to infinity, so the sum of the ith row of the theta matrix should be equal to the sum of the ith column, and that should be just equal to the invariant probability of state I for every I. Now, when we have access to data, we don't see the true theta. We could use an estimator to estimate this doublet distribution, and the natural choice is the empirical doublet distribution, whose definition is shown here. So element ij just records how often in the data set we see a direct transition from state I to state j. And again, by the Fisher-Neiman separation theorem, this doublet distribution is in fact a sufficient statistic for theta. And it is also known that this doublet distribution satisfies a large deviation principle. And in this case, the rate function is no longer the Callback-Leiber divergence, but it is the conditional relative entropy, which is a bit less known. The definition is shown here. It's related to the Callback-Leiber divergence. But bottom line is, what this tells us that if you have Markovian data, then we can solve the full-blown meta-optimization problem over all predictors and prescriptors, and the optimal Pareto-dominant predictor will be a distributionally robust one, where the ambiguity set is described by this conditional relative entropy, so a ball around the empirical doublet distribution with respect to this conditional relative entropy. So that will be the Pareto-dominant solution. So I'm going to be quick now. So we've also looked at some autoregressive processes with infinite state spaces. So these are Gaussian processes. So the noise here is always Gaussian. In the first example on top of the slide, you assume that the drift term theta is unknown. And it turns out that some scaled version of the sample average of the historical data, so a scaled sample mean satisfies a large deviation principle, but is not a sufficient statistic for this theta. Which means that in this case, we can solve the restricted meta-optimization problem. We can find a Pareto-dominant solution for that one, but we do not know whether this would be also a Pareto-dominant solution for the original problem. We cannot solve the original problem in this case, the full-blown meta-optimization problem. Similar thing happens when in the second example that we could address. So this is a stationary Gaussian process, autoregressive process, which is actually a scalar one. And what is unknown is the coefficient, the autoregressive coefficient here. And there are two different estimators for this theta that satisfy a large deviation principle. One is just the simple least squares estimator. And the other one is called the Yule-Walker estimator. They satisfy different large deviation principles with different rate functions. And that means, in this case, again, we can solve two different versions of the restricted meta-optimization problem. We can find Pareto-dominant solutions, but both statistics are known not to be sufficient. So again, we cannot actually solve the original meta-optimization problem in this case. Last example is that of where the training samples are i.i.d, but the cumulative distribution functions of the individual observations, they belong to some parametric family, like normal distributions, exponential, gamma, Poisson, Bernoulli, geometric, binomial, and so on. The list is not exhaustive, so there are many that work. In all these cases, the sample mean turns out to be a sufficient statistic for the unknown parameter, and it satisfies a large deviation principle. And actually, the rate function is that is relevant here is the convex conjugate of the log moment generating function of the distribution of one observation. So this is a general result. It's basically Kramer's theorem. And that means that in all these cases, we can solve the original meta-optimization problem. We can find Pareto-dominant solutions. And we will get many very different distributional bus models. And in fact, many convex uncertainty sets that have been considered in the literature, they could be explained in this way. So the corresponding predictors or distribution robust models, they could be interpreted as the optimal or Pareto-dominant models for certain structural properties of the data generating process. So actually, our theory somehow gives us a way to distinguish between different ambiguity sets or uncertainty sets in robust or distribution robust optimization. People up to now, more or less, they use ad hoc arguments to say, but this one is a good one, this one is a good one. So here we could really relate the geometry of the uncertainty set to the structural properties of the data generating process. Okay, so I guess there are probably other examples of data generating processes that satisfy these properties, like an LDP or sufficient statistic or not. So far, these are the ones that we found and that we've studied in the paper. But let me now wrap up the talk with a small summary. So we've seen that in data-driven stochastic optimization, we do not have access to the probability measure that governs the uncertain problem parameters. We only have access to training data. And that means we cannot solve the original problem. We need to solve a surrogate optimization problem. And we've proposed an optimization problem that in some sense tries to find the best surrogate optimization model. So it's an optimization model that optimizes over predictors and prescriptors, or over surrogate optimization models. And this meta-optimization problem balances in-sample risk versus out-of-sample disappointment, simultaneously for all possible parameters theta that encode all the possible different probability measures. And if you have a Pareto-dominant solution for this problem, then it implicitly pushes down the out-of-sample risk of the data-driven decision. So we've seen that if such a Pareto-dominant solution exists, then there is a separation between estimation and optimization. So we can first construct the statistic and then solve the DRO problem. And this result is somehow reminiscent of the classical Rao-Blackwell theorem. The Pareto-dominant solution, if it exists, is a distribution robust model. The ambiguity set is a rate ball with respect to the rate function of the large deviation principle. The ball is centered at the statistic theta t, and the radius of the ball is equal to the decay rate of the out-of-sample disappointment. And this result is in some sense invariant under homeomorphic coordinate transformations in the model space and also in the space of estimators. So in some sense, one could interpret these results as representing some sort of efficiency or some data efficiency. In fact, the Pareto-dominance property of our optimal data-driven prescriptors and prescriptors, they're reminiscent of the so-called concept of Bahadur efficiency, which has been studied in statistics. So usually in statistics, if you talk about an efficient estimator, you mean that it attains asymptotically the best possible variance. I mean, this only works for unbiased estimators in the sense that the variance after a proper scaling attains the inverse Fisher information matrix. And so Bahadur had a different notion of efficiency, which is not with respect to small deviations, but to large errors. Like here, we use this large deviations theory, and somehow it seems that our methods are related to this efficiency concept. So we could say that the distribution robust predictors and prescriptors we obtain, they are in this sense, in statistical sense, they're efficient. The results here are actually quite general, and I never used any convexity properties of the decision problem. So our decision problem can be non-convex. We did not insist on the training samples to be i.i.d. So we've seen examples where the training samples actually are non-i.i.d. And yeah, overall, this work, what we try to do is somehow to give a theoretical justification of using distribution robust optimization models, and in some sense to relate the shape of the ambiguity set that you should use to the structural properties of the data generating process. The radius of the ambiguity set also has a nice physical interpretation as this that relates to the auto-sample disappointment. I didn't talk about computation, so through this work we came up with some distribution robust optimization models that have not yet been studied, and one would have to develop to see whether they can also be efficiently evaluated. So we've looked a bit at the conditional relative entropy DRO models that emerge in the context of Markovian data, and we basically try to develop some algorithms for solving these models efficiently. But that's something that I didn't have time to talk about. So this brings me to the end. I'd like to thank you very much for your attention. The main references for this work are listed here, and really the paper that I presented is paper number 3 in the red box. Yeah, so this is the end. I'd like to thank you very much, and happy to take more questions.
Thank you so much, Daniel. So we're a little bit over time. I know some people have to go, but those who want to stick around and ask some questions, maybe we'll take a question or two. And since we're a bit over time, may I suggest that if you have a broader general question that might be of interest to many, please speak up. And if you have more specific questions, maybe you can follow up with Daniel afterward.
So, yeah, if I may, I'll jump in there. So thank you, Daniel. This was really fun and really interesting. I like this kind of overall structure of minimizing the expectation subject to some kind of constraint. But I had a similar question to Sid, actually, about your choice of using this probability in the constraint. It's sort of interesting that you minimize an expectation, but then you have this constraint, which is essentially on the distribution as opposed to, say, a moment or something. And I was curious what, because you chose it that way, you end up with this quite tractable conclusion, which is really quite lovely. But I'm wondering if you were to have changed the constraint to an expectation or a quantile or something, would similar kind of conclusions be possible?
I'm not sure, because we heavily rely on the large deviations principles. And of course, there we need to deal with probabilities, because the large deviation principle tells us something about the exponential decay rates of probabilities. So that's the reason why we chose this. I think empirically it does make sense in view of the example I've shown, where really this probability, when we evaluated it empirically, it did decay exponentially. And well, actually you can prove using the large deviation principle that if you have a set that doesn't contain the true distribution, then its probability will decay to 0, and it will do so exponentially. So actually focusing on this exponential decay in that setting is not a big of a restriction, actually. Now I guess I'm not really answering your question. So yeah, having this so the constraint looks difficult. So it's an asymptotic exponential decay rate. So there's a lim sup, and there is a log, and there is a probability. So this looks like in terms of optimization terminology, that is sort of an asymptotic chance constraint, which is usually completely intractable. But I guess it doesn't matter because we're not using optimization technology to solve this model. We're solving this model analytically, and we see what the optimal solution is. The optimal solution is itself an optimization model, and that one we will eventually have to solve analytically. But
yeah, I think I appreciate why you're using large deviations here, because you can then use all of the machinery from that sphere. It feels just like it's somehow an asymmetry that is interesting. And the fact that you're dealing with problems that all come from the exponential family, I think, means that you're able to exploit a lot of machinery from the natural exponential family there.
Absolutely. So actually, I didn't go into discussions of exponential families, but Theorem 2, there the way we prove it in the paper is that we assume that there is an exponential family. When we deal with sufficient statistics, then at least in the i.i.d. case, this is equivalent to dealing with an exponential family. And this is the Pitman-Damois-Koopman theorem, I think. And probably, I'm not 100% sure if we have non-i.i.d. data, but probably there's also a very strong connection between having a sufficient statistic and dealing with an exponential family. So we proved it right away under the assumption that the family p theta is an exponential family. And then we used reduced, so in this case, well, basically all models, all exponential families, they have these properties: sufficient statistic and large deviation principle.
Great, thank you very much. Yeah.
Thank you.
So one follow-up to the comment about the exponential family. It also seems like, or again, alternate way of deriving this would have been under some sort of a maximum entropy principle, that you want to sort of maximize your objective under a family of distribution which is maximum entropy subject to some constraints. And that would also naturally give exponential families by sort of the same logic. And
I'm not sure whether we're really doing something with the maximum entropy distribution here. We're just trying to simultaneously optimize over all distributions.
What I'm saying is more, if you put a max entropy constraint, that would also naturally lead to this sort of like an exponential family as the solution, and sort of solving under an exponential family. I don't know if there is a connection, or it's sort of intriguing.
I'm not sure, because we're not optimizing over the distributions, right? In the meta optimization problem. So we optimize over the models, over the optimization models constructed from the data. And we want them to perform well under every possible distribution in an exponential family.
Oh, I see. Okay, yeah.
Mm-hmm. I'm sure there is a connection actually, but it's probably somehow different. So
yeah, I mean, it's a beautiful solution. Like, it's surprisingly clean in the end.
Thank you. Yeah, it has these weaknesses which I mentioned. I think, yeah.
I like large deviations.
I would like to.
I'm happy.
Yeah. We would like to address some of these weaknesses. So, for example, the condition of a sufficient statistic is admittedly this is a strong assumption because it restricts us to exponential families. That is restrictive. But since the performance measures we're using, they're both asymptotic, we believe that we would probably get away with an asymptotic notion of sufficiency. And it's something would be very interesting to see whether one can relax that.
Since the DRO stuff you end up with are all kind of this log odds ratio type stuff that come out, like KL and the conditional entropy thing. So one question, I mean, we know you love Wasserstein distance. That doesn't really come up, or does it come up in the least squares thing? The least squares one?
No, actually, I mean, we also thought, is it possible that the Wasserstein distance, the Wasserstein DRO problem is optimal in some sense? And we couldn't figure it out. So it seems that in terms of these criteria here, so far, we don't know about it. Actually, Bart has looked into this
distribution thing where you can't do this parametrization, right?
Sorry. Can you repeat, please?
I would say the Wasserstein DRO thing probably makes most sense in the continuous setting where you can't do this parametrization. Because as soon as you can parametrize, it's all this, you know, in their sufficient statistical exponential families, it's always going to be like some like KL-like thing.
Although, actually, yeah, it's true. But I should like to point out that I believe that, so we are restricted to finitely parameterized families here, just because this gives us a clean framework. But we have looked also at non-parametric cases in the simplest case, so where we have just i.i.d. data and where the data can be generated by any distribution on some polytope, say. And in this case, a sufficient statistic is actually just the empirical distribution as a mixture of the crux, right? And actually, Sanoff's theorem extends to that case. So we still have a large deviation principle, and we can still actually prove stuff. And that's something that we've done in this paper here, reference number 4. It gets very tricky there, because in the large deviation principle, you have the closure of D and the interior of D, and so there's lots of topological questions that come into play. And also, I swept under the rug these properties of the rate function that we need. Actually, what we need is some sort of certain continuity properties in one component, and level compactness, and to establish these things in an infinite dimensional space is difficult. First of all, you need to agree on the topology you're using, and then it gets very, very messy. So, or at least, I mean, for me, I'm not used to these kinds of arguments. I think we managed to some extent for i.i.d. data. I would believe that sort of the basic ideas should go through in more general settings, but we haven't yet been able to fully generalize everything. So.
Okay, thanks so much, Daniel. That was really, really interesting and exciting. Looking forward to chatting with you.
Thank you very much. Yeah, sure.
I've written down a lot of questions.
Yeah, so. and of course, this is very recent work. So any feedback, highly welcome.
Really, really, really cool.
Thank you. See you later. Bye bye.